No questions on the exam. Cool. All right. Well, let's jump into ODPs.
Can you cover, I guess, Linux stuff?
Yeah.
Or like what you need to know, because I'm sure I use a lot less than what you've taught in class to do everything.
So what's a good set of Linux stuff to know? So make dir to create a directory, pwd to see what directory you're in, cd to change directory. Doesn't hurt to know ... which is how you get to a parent directory. So if you're down one level, you can cd ... to go up. ls to show the contents of a directory. ls-l if you want the long contents that show you like the size of the file and the date and that kind of thing. cp to copy a file, mv to rename or move a file, rm to remove a file, rmdir to remove a directory, gcc-o output, source.c to compile a file. That's a pretty good start. Let me see what I posted. Oh, change mod to set the permission on a file. So like change mod 755 to make it executable is the only thing we've really done. Move, copy, remove. I'm not going to ask you about word count and date. I'll play with them later. Definitely echo to do output, and read to do input, and variable equals something to give a value to a variable. I think that's probably a sufficient set of Linux commands. There's more stuff when you're in shell scripting, like ifs and so on, but as far as things you might do from the command line, that's probably plenty. So it's not a lot of fancier stuff.
So we can bring 4 pages?
You can have 4 pages double-sided, or you could do 8 pages single-sided if you wanted for some reason.
So the size of pages?
No specification. You could bring in like a giant sheets of paper if you want, but you got to negotiate with who's sitting next to you. My goal is not to make you choose what to put on your notes. I'm not trying to limit you, but in the past, if I say open note, people come in with 3-ring binders and they spend the whole time flipping through trying to find their answers instead of just putting down what they know. So I put a limit on there just to let you choose what you want to bring, but it shouldn't be restricting you. As far as I really want to put this on my note sheet, but there's no room.
I was wondering why you said 4 pages. Maybe you're...
Yeah, no, you shouldn't. I don't think you would need 4 pages double-sided of notes, right? Particularly if you've been doing this stuff. But you know, if you can never remember the format for an if statement, definitely put one down on your notes, or a while loop, or if there's some mistake that you tend to make a lot in your code, you know, use 2 equals for comparison, put that down on your notes. But I suspect I could make it closed note, closed book, and people would still do pretty well. So. All right, yeah.
Do you have time to like go through the steps for compiling this?
Yeah, we got plenty of time.
On that note, does the -c just mean don't expect the main? Or?
Yeah, so we'll talk about that too. So let's make just a sample program. All right, so this is my hello world code.c. Um,
Yeah.
Cool. Thank you. By the way, when I'm doing that, I'm doing an XP. X will delete a character, and P will put it after the current cursor position. So a quick way to reverse two characters is just XP. Okay. All right. So the usual way that we compile this, and if you know this, you're good to go. GCC-O, and then the name of the file that you want to create is an executable file. Okay, so this would typically be called code, but it could be called main, it could be called PA5, it could be whatever you want the executable program to be called. I'm just going to say code, and then you list the source files that you're going to compile. And when you do that, it creates one file called code, and that's the executable version of your program. So for the most part, that's the only thing you need to, the only version of GCC you need to know. If you don't do this -o, if you just say gcc code.c, that compiles it, but it makes an executable called a.out. And every time you compile a program, the executable is called a.out. So putting in this -o just says, let's call the executable something different.
So where does -c come into it?
We haven't really had to use -c yet, but we will in a week. But if we say, so here's my code.c. If I say gcc-c code.c, I don't get an a.out. I don't get an executable. I get this code.o. Okay, so here's what's happening when you want to compile a program and execute it. There's actually a few things going on. So you've got your source file, which is code.c. And we run GCC on that, and it gets compiled to something called code.o. That's what we call an object. And an object module is still gibberish to us, okay? But we can't run it. It's not executable. And even if we make it executable, if we try to run it, can't execute exec format error. It's not a runnable program. Okay, it's an object. And then there's this library which has things that are included in standard I/O like printf and all of that stuff. All of that code is sitting in some library, and the contents of that library in code.o have to get put together to make an executable. And this is actually done with a program called LD, load. But when you say gcc-o code.c, all of this happens automatically. When you say gcc-c, you're just saying, just do this one piece, just make me a code.o. And then I could take that and I could link it with the library and maybe some other stuff to make an executable. And that's what we'll be doing with program 4, is we'll be making these things in separate pieces and putting them together. But for everything we've done up through today, we can just do this gcc-o and everything gets built into an executable. All right, other questions? Yeah.
Would it be -LD? Because that.
No, LD is actually, it's its own command. And I've used this a few times when I was curious about it, but I've never actually used it. Because in practice, if we have a code.o and we want to link that with the runtime library and make an executable, we can do the following. We can just feed it to GCC. And I don't need my .c file at this point. My compiled.c file is code.o. Just by using code.o and feeding it to GCC, GCC will call this LD program, this loader, and make an executable. And then I can run that. But what's happening under the hood is it's calling the linker. And linkers are mysterious things to me, at least, because you're pulling in all this stuff from other places, and it's a cool process.
What's the difference then between having, I mean, I understand the linkers involved, but what's the difference between having multiple C files that you tie together to run in one C program versus having, like, what's the advantage of having an object file, I guess?
Yeah, so this will be a topic of much discussion next week. But let's preamble. So we got 3 C files, and we want to put them together. Okay, if we say gcc-o main, and we list these files, each of these get compiled. And then those get linked together to make main. Okay, if I type in this command, gcc-o main, right? GCC basically compiles each of these C files into objects and then links those objects together. But instead, if I do the following, gcc-c f1.c, right, which gives me f1.o, f2.o, f3.o, and then I use GCC to link those together. Here's the advantage. Suppose I make a change to f2.c. I can run that one command just to compile f2.c, create a new f2.o, and then link these together. I don't need to recompile f1 and f3. But if the way I'm building my executable is with this big long command here, I make a change to f2, when I type in this command, f1 and f3 also get recompiled. So the end result is the same, but this is doing more work. It's compiling code that I didn't actually change. Why? Because I said compile f1.c and f2 and f3. But if I had 100 files and I only wanted to change one of them, I could change that one file and just do gcc-c that file. That gives me that file.o. I already have my .o's for my other files. I don't need to recompile those files. I can just take those 100 .o's and link them together. And linking is relatively fast. It's reading binary code and it's creating binary code. That's pretty efficient. Compiling source files, we've got comments and spaces and all kinds of stuff. That's a relatively slow process. So now think of a project with 100,000 pieces to it. And you change one file. Do you want to recompile 100,000 files or one file? That's where it really makes a difference. So when you're working on a large project like Linux, for example, where you're writing the kernel or something and it's got thousands of different files, we want to be tactical in what we choose to compile. And there's a tool that will help us do that. That's called a makefile, and that's what we're going to talk about next week, along with other things as makefiles. But for the midterm, don't worry about any of that. Just gcc-o executable file source code. The other thing that, since we mentioned linkers, the other thing that linkers do is you know, in your main program, I said, let's call this function named printf, and I didn't tell it where the code for printf was. The code for printf was already written by someone, already compiled by someone. It's sitting in the library. Well, somehow the compiled version of this code needs to know that it's supposed to call wherever that printf function ends up being situated in memory, right? So it's not only got to grab that printf code and say, okay, let's store this here in memory. Now it's got to go back and it's got to adjust things like this call to printf and say, oh yeah, when you call printf, that's over at location blah, right? And it's got to set up the call to say call blah. And same thing with global variables or things that are defined outside of this file. It's all got to get linked together. So that's really what the linker is doing. All right, other questions? These are good. Does anybody know what was going on with traffic today? Other than there was a lot of traffic, was it accidents?
There was accidents on like 205, I think,
Yeah.
between here and Morgan.
Okay. All right, so let's look at ODP 415. So this was the calculator code. So there's a function calc, takes a character array, returns an integer. You need some temporary variables for the result of scanf, so n1, n2, and op are the two numbers and the operation. And then we just lean on scanf to do the heavier lifting for us. So buffer is the argument that got passed in, so we run that through scanf. And we ask for an integer, a character, and an integer. We store those in n1, op, and n2, and we save the return value from scanf in this variable called stat, or status. If this works correctly, scanf will return 3. Why is it 3? Because we've got 3 things with percents in here. We're asking for an int, a character, and an int. That's 3 things. It will return either -1, 0, 1, 2, or 3. If it only matches an integer and it doesn't find a character after that, this will return 1. If it finds an integer and a character but not a second int, it'll return 2 because it found 2 things. If it finds all 3 things, it'll return a 3. And if the line buffer was actually empty, I think then it'll return -1. If it doesn't find an integer in the beginning, it found nothing, it'll return a 0. So it can return a lot of different values if something goes wrong, but only one possible value if everything goes right, and that's in this case 3. So if you want to know if there's a syntax error, your check should be, is the status not 3? You could say if the status is -1 or 0 or 1 or 2, but it's easier to just say if it's not what it should be, which is 3, then return the syntax error code -1. Okay, if we get past that if statement, we know that we had an integer, character, integer, and they're stored in n1, op, and n2. And so now we need to do whatever the operation is telling us. So I went with a switch statement, but you could do this with a set of ifs. So if the operator, so switch takes a character or an integer, something simple like that, and you have a series of statements that say case, and the first case where the thing that you specified after the case matches the thing in parentheses here, the statement will be executed after the colon, and it really executes all statements after that. So this switch statement is basically saying, look at OP, that's the operator, if it's equal to a plus sign, then do this. And since it's a return, it doesn't go on and do anything else in the switch statement. Okay, the return exits the function. So if the operator is a plus, return the sum of n1 and n2. If it's a minus, return the difference, and so on. And then default is a special keyword which says if you come through all the possible cases and you didn't match any of them, here's what you should do. And in that case, it means the operator was not one of these 4, so we return the invalid operator code. But if you don't like switches, right, ifs work just as well. If you do like switches, remember that usually if you're not returning, you need to have a break statement before the next case. Otherwise, it'll just fall through and execute the next case. All right, and there's definitely no fgets or anything like that in here. We're not reading anything from the user. We're just processing an argument, which is a string. But we do need scanf because we're trying to interpret it as a pair of integers. And if that's not making sense, go back and write some more test code with scanf. Just start scanning different things with different patterns and look at the return value. And once you see it in a few examples, it's usually pretty clear what scanf is returning. Right? It's basically the number of things that it matched from your expression. And remember, scanf gives up pretty easily. If it does not find an integer here, it's just going to return a 0. It's not going to look for a character and an integer after wherever it is. If it doesn't find an integer in the beginning, it's done. Didn't find anything. If it finds an integer but not a character, it'll give up after that first integer and return 1. So it starts at the beginning of the string, tries to match according to your pattern, and as soon as it fails, it stops. And it returns a number telling you how many things did match, up to the point where it gave up. So questions about this? Alright, so let's look at 416. The 416 is yet another string processor. It's called rem, as in remove. And it accepts two strings. The first string is a string of text. The second string is another placeholder. So it's like ODP 414. We're going to write into the second string. And what we're going to write is a modified version of the first string where we removed all of the lowercase x's. So the intended behavior is pretty simple to describe, but the code not necessarily as simple. So remember, if you're writing your test code, your second argument has to be an array that has some space, enough space to store this string with the x's removed. So if I call rem with this string and I pass a temp and then I print out temp, it should print HEHAOHO. Alright, so it's this string without the x's. If I pass it a string that contained two x's, it should return a string that's empty. No characters in it at all. And again, new lines are not special. Letters, digits, punctuation, no characters are special. Just read each character, and if it's an X, don't put it into the output string. If it is an X, put it into the output string. Don't replace it with a space, remove it, right? So if your input has any X's, your output's going to be shorter. So you got to do some work. But the work is a pretty simple algorithm, for us at least. So if you know what your input string is, and there's a null terminator on the end, so this is our input. We'll build your output one character at a time, just like we've done in other ODPs. So you need a pointer for your input, a pointer for your output. Look at your first character in the input. If it's not an X, add it to your output. Look at your second character. If it's not an X, add it to your output. Look at your third character. It's an X. Don't add it to your output. Just go on to the fourth character. That's not an X. Add it to your output. Right? But you need a separate counter here from what you have here, because this is not always going to go in the same position that you read from because your string is getting shorter. So just make a pair of pointers, one for input, one for output. March through here in a for loop or a while loop, and your output, when you decide to add something to it, bump up the output pointer, the index. And when you're done, right, you'll have read an O and you'll have written an O. If you bump up your index afterwards, it should be pointing right here. When you get to the end of the string, tack on a null terminator and return. So everyone think they can do that? Awesome. All right, it's another int function where I don't care what value you return, so return any integer you like. You can use the string length function if you like, but don't use any other built-in functions like the remove x from string function. You gotta write it yourself. All right, and then link it in with the test bed and the SSH. All right, questions on any of this? Yeah.
Also about ODP 415, you said that if argument line has nothing, it will return -1.
That should return whatever the syntax error thing was. So yeah, that should return -1. Yeah, because it doesn't match character integer, or integer character integer.
But so the -1 is because of scanf will
Yeah, if scanf doesn't return 3, then your function should return -1. Because there's two types of errors. The first error is it's not in the proper format, which is supposed to be number, character, number. Right? So -1 says it's not a number, character, number. -2 says, yeah, it is a number, character, number, but that's not a good character. It's not a plus, minus, dash, or plus, minus, star, or slash. So it's just recognizing two different errors.
it returns -1 because we say it returns -1
Mhm.
or it automatically returns.
Because we're saying return -1.
So if we don't say it, what value it will be returned?
If you just say return, or if you just fall off the end of your function, it's pretty much unpredictable. All right. Well, let's switch gears. So what we're talking about here will not be on the exam tomorrow, but this is stuff we're going to use heavily in PA4, and then you're going to use it even more heavily in winter in 222. So I want to talk about debugging. So, you write your code and you try to compile it and you get syntax errors. And sometimes you get 1 error, sometimes you get 90 errors. And sometimes you're missing a semicolon and that breaks everything. Or you're writing a comment with like /* and a bunch of comments, and you forgot to say */ at the end. And you've accidentally commented out a whole bunch of your code until later on, halfway through your file, you have another comment that says /* and then it says */, and that ends that first comment. And now you're missing a whole bunch of function definitions, and you try to compile your code and you get like 100 or 200 errors coming out. and it's just because you put a space between the slash and the star, right? So you work through these things, and eventually your program compiles. Okay, so those are one type of error. They're compile errors. Okay, it's usually related to syntax. Once your program works, once the compile errors are gone, your code still may not do what you want it to do. So it can still have runtime errors, and runtime errors are things that happen when your program is executing. Okay, compile errors, GCC will figure out. You didn't have a semicolon, you've got a variable you didn't declare, something like that. Runtime errors, everything works. You have a runnable program, you run it, and it blows up, or the lights go off in your house or something. So it's got some kind of bug associated with it. So debugging is usually talking about trying to find runtime errors. Okay, something's not doing what it's supposed to do. I usually mention this in Engineering 250, but if you haven't seen this, you should, right? So, so this is the first recorded case of an actual computer bug. Right. So this is a moth taped into a log book, and Admiral Grace Hopper, one of the first programmers, was working on a very early computer and working on a cosine function, and the answers weren't coming out correct from the program. And she was tracking it down, running test cases and so on. And eventually she went inside the computer, because computers were big enough you could walk inside them, and it was a room filled with racks of cabinets, and she traced it down to a cabinet, so panel F, relay number 70, and she pulled out that relay and it had a moth stuck inside. So a relay is like a transistor, but it's about this big, and it's got a piece of metal inside, and it's got a spring that's pulling the metal one way, and it's got an electromagnet that's pulling this piece of metal the other way, and that's how it opens or closes. And somehow a moth had gotten inside the plastic case covering this relay, and when the metal was trying to move, it couldn't move because there was a moth body trapped in there. And so this was basically a defective relay, defective transistor. And of every transistor in your laptop does something. And if one of those doesn't work, there's a good chance you'll eventually discover something misbehaving. And in this case, it was this math function wasn't giving the right answer. So she actually found this bug and then taped it into her logbook. It's the first actual case of a bug being found. But that's really what debugging is, right? It's here's my code, here's the computer, here's what should happen, it's not working, where's the problem? It's trying to narrow down the problem to the one specific thing that's actually causing it, the root cause. And for us, it's usually a problem in the way we wrote the code rather than a moth in the laptop. So how do we do that? How do we find where the problem is that's causing this thing not to work? And that's the art of debugging. So, and to me, it's an art form. It's not something that we can write a step-by-step guide to. Do this, do this, do this. If this, go over there. Otherwise, do these things, and eventually you'll find your bug. It's something that's learned, and you develop a feel for it, and you have hunches, and you follow those hunches. But what you can learn is how to get better at going through the steps that you feel like you want to do to find a bug. Like, I think something's wrong with this function, but I don't know what. How can you figure out if that's a valid hunch? So that's a learnable part of debugging, and we're going to talk about some tools for doing that. The main tool we're going to use is something called GDB, and that's the GNU debugger. And it's a standard part of Linux. If you have a Raspberry Pi, it comes with GDB. And if you have an old Linux system, it comes with GDB. But it's also on, my laptop system. And so if you learn how to use GDB, you can use it in a lot of different situations. And even if you have a tiny little computer system, like something running inside an embedded system like a watch or something, it may still have GDB on it because it's a really small program and it's really useful. If you have an Android phone, you can use the Android debugging bridge, similar idea, and you can get inside and see what's going on in the processor. So these are general concepts we'll talk about. So to use something like GDB, you need to understand the program you're trying to debug. So it's hopefully not totally random code to you that you just wrote to see if it works, right? Hopefully you've got an algorithm in mind, you've got some steps that you're thinking this code should follow. And what GDB will let you do is watch what happens as your program executes line by line. And you can do two things. One, you can see, you said if such and such, then call this function, and you think it should call a function, but you say go on to your next step, and it doesn't call the function, right? So you can track the flow of your code and say it should have done this, but it did that. Or it should have looped 5 times, but it only looped twice. So you can follow the flow and sometimes find problems like that, but you can also examine memory. And you can either look directly at memory or you can examine variables. So I should be equal to 0 here. You can print the value of I and say, oh, I is equal to 17,000,005. Something's wrong. Maybe I forgot to initialize I. So it lets you examine the environment, the mind of the computer, if you will, as your program's executing. The third thing you can do, and this is less frequent, is you can make changes to that environment. You can say, oh, my flag should have been set to 1 to start with. Well, you can say, okay, set the flag to 1, and then start stepping through and see if that fixes the problem. But usually when you find a problem, I should have initialized the flag to 1 and I didn't, you get out of the debugger, you go back in the editor, say flag equals 1, compile, link, test. And if it doesn't work, then you go back in the debugger and you continue. Debuggers usually work pretty well. Occasionally they have the bad habit of fixing your bugs for you. And this will happen more in 2.22 when we're dealing more with dynamic memory. This can happen and it's really frustrating. You've got your program and you've got a test case, and every time you put in these inputs, you get a seg fault. Okay, so let's use GDB to figure out what the problem is. Well, you run your program with the debugger and you put in your test case and it works perfectly. It doesn't seg fault and it actually gives you the answer you want. That's a really bad situation because now you can't use your debugger to find the bug because there is no bug when you're using the debugger. It's only when you take it out of the debugger that you have a problem. That's a whole different situation. That's not going to happen to us here probably. Okay, that's usually when you're doing something like going out of bounds with an array or something like that. I had that happen to me with hardware once. I was building a board. It was about this big, had a few hundred chips on it and just this rat's nest of wire in the back, and something wasn't working right. And it was sitting in a rack with all these other boards, so the boards were about that far apart. There's no way to measure voltages and stuff. So I got an extender card that you put in the rack, and now the board that you're working on is sitting outside the rack. Well, it started working perfectly. So if I had it on the extender so I could debug it, I didn't have to because it worked great. But when I put it back in with the other boards, it was malfunctioning. So there was no way to debug it like that. So that can happen in code, but that shouldn't happen this quarter. It might in 2.22. All right, so let me modify this program a little. to give us more stuff to play with. So there's an attempt at, and I'll get rid of this because I want some bugs in here. All right, let's say we've got this code and it's not working right. Right. In particular, I don't have code that's checking for a syntax error. And I want to know what's going on. Alright, so there's my calc.c. I'm giving it an error 23 equals 57, and when I run it, instead of giving me an error code -2, it gives me this result, which is just some weird big number. And I have no idea what's going on here, right? So I want to debug it. Okay, so we're going to use GDB. And first thing you want to know is when you compile your program, well, let me do this first. I can just say GDB in the name of my program I want to debug. And if I do that, I get a bunch of stuff up here, but I get this message at the bottom. Reading symbols from calc, no debugging symbols found. Okay, I can still debug my program, but for example, if I try to list it, I can't see what my code looks like. If I try to print the value of I, it doesn't know what the variable I is, or the variable stat, which is a return from scanf. Right? It's really hard to debug. So I have to do something. If I'm going to try to use GDB on a program, I compile it slightly differently. Normally we say gcc-o, executable name, source code, add one more switch, -g. So that -g says include debugging information. Yeah.
Is it okay to do that even if you already compiled it the other way?
Just recompile it again. Yeah. Okay, so this works the same as before, and I still have an executable program named calc, and I can still run it, and it should do the same thing as if I hadn't put in -g. The only difference is calc has extra stuff in it now. So let's see. If I just compile calc the old way, gcc-o calc.c, my executable program is 8,432 bytes long. If I compile it with debugging information, it's 11,120 bytes long, so it's larger. It's got extra stuff inside, but still not that big. Okay, if you want to debug your program, you say GDB and whatever the name of your executable program is. So this starts the debugger. So I'm going to say GDB calc. And you get all the stuff up front, which is like, license information and the version and that kind of stuff. But this last line says reading symbols from calc done. Okay, so it found information in this file calc that it will use for debugging. If you do this and it says no debugging symbols found, then you probably forgot the -g switch, or you're trying to debug a different program from the one you compiled. So it should say reading symbols from calc done. And if I say list, it'll show me my source code. Well, the first 10 lines of my source code. Okay, so a couple of things about working with GDB. Enter repeats your last command. So I just said list and it showed me the first 10 lines of my file. If I just hit enter, it'll show me the next 10 lines of my file. And if I hit enter again, it'll show me the next 10 lines while there were only 4 lines to show. So it's at the end of my file. So I can look at my source code, which is nice. Okay, if we want to start running our program, we can say start. And it always puts what's called a temporary breakpoint at the beginning. So start is how we start debugging. Now, if it just ran our program, we couldn't debug. We wouldn't be able to look at the values of variables because our program would be running. And if we said print the value of the variable I, well, if we had an fgets in here, that would be the input to fgets, right? So when we say start, it starts off by prompting us, GDB in parentheses, and it says, tell me what you want me to do. And I can say things like print the value of I, while I is equal to 0. It hasn't executed this call yet. Okay, statement 7 is about to be executed, but it hasn't run yet. I can say let's print the value of n1, and it doesn't know about n1. Right? Why? Because there's no n1 inside main. There's an n1 defined in my function calc, but we're not running calc right now. We're about to make this call to calc. All right, so usually what you're going to do is you're going to try to step your code one instruction at a time. We're going to say, let's go ahead and run forward one step. I'm going to say step, and this should make a call to my function calc. So if I say step, it tells me, okay, now I'm at line 12 in calc, calc.c:12. That's this curly bracket right here. And it tells me that I'm in a function named calc, and I have an argument named buffer, and buffer is equal to this thing. Well, that's a memory address. And it knows that's the address of a string, so it's also showing me the string at that address. It's 23 equals 57. That's what we passed to calc. So I'm about to start executing my function. And if I say step, well, there's nothing executable to do for integer n1, n2, character op, integer result, or blank line. So it comes all the way down to line 17. And it's about to do this scanf. So if I print n1, n1 hasn't been given a value yet. So n1 just has random stuff in it. n2 has random stuff in it. op has random stuff in it. So I can say, let's go ahead and do this scanf. Okay, I don't want to debug the scanf function. If I say step, it's going to start executing the instructions of scanf. I don't want to do that, so I'm going to say next, which says go down to the next line in my file. And now I'm back here, so now I can say print n1, that's the 23, print n2, that's 57, print op, that's an equal sign. So it's executed this call to scanf, and it's back, and it's about to start doing my if statements. All right, we're out of time here. We'll keep going with this next week, and we'll be spending a while working with GDB, so this is just kind of a warm-up to it. All right, I will see you tomorrow.